Good evening, I'm Apurva, and this is week 12 of Stochastic Control and Communication. So, let's take a quick recap of what we talked about in the last tutorial, and then we're going to focus on this week's tutorial. So, last week, the focus was not on normal, not on regular control problems, but rather on problems where there are multiple agents who are working together or more like a team. Okay, one second. There's some network error. Um, okay. Okay. So this is a quick recap of week 11, and then we'll start with week 12's tutorial. So in week 11, we talked about uh, problems with more than we focused on the interpretation that each time step is basically different controllers, and also that those controllers are trying to work together as a team to optimize that common optimization problem that they have. The thing is, each of them has to take a particular action, and to take that action they have some information available to them. So in that kind of a setting, if we have n agents and it's taken at t time steps, then instead of looking at n agents and t time steps, we could look at it as n times t agents. So time is not that important, but the information structure becomes of importance, as in what is seen by each agent and at what time. So we saw if this is something that depends only on the state of the world or the noise term, then such a problem is called a static team problem. If that is not the case, meaning if the information also has some information about the actions taken by other agents at other times, most likely times before the current time, then if all of that is also included, then those are typically called dynamic teams. Uh, Last time we focused mostly on static teams only. We saw a few examples and we saw what happens in different types of information structure in these games. So we saw these variations. If the two agents, for example, if it's a problem with two agents, then what if they have perfect information and the information is same for both of them? Then this is a very easy problem to solve. On the other hand, if there is imperfect information but identical, same information is available to both of them, then it's slightly harder than the previous one, but still, because of identical information, it can be thought of as just one agent only instead of multiple. On the other hand, if the information is not identical, then the problem starts becoming more interesting, and each agent has a different role to play because they have different information. Then that starts showing up. Also, we saw two concepts, one of team optimality and another of person by person optimality. And we saw a theorem which said if the loss function has certain properties, that is strictly convex and continuously differentiable, then person by person optimal would also be a team optimal solution. And this is something that is true specifically in LQG games. There may be other specific team games where it may be true, but the focus, one particular example where this theorem holds is LQG games. So this is the things that we talked about last time. And then the things that were the last point in last week's lectures was Witsenhausen's counterexample and how does that fit into the whole framework. So this is how I'm starting week 12. So Witsenhausen's counterexample has some initial information x0 based on which the controller picks up a policy and takes an action. Now this policy affects the cost directly because the cost has this u1 term show up. Another thing that this policy does is it affects the information that is available to the second agent, and that information ultimately affects what policy is chosen by the second agent or the second controller, and then finally what action is taken. So this was a scenario of dual effect. Now notice, whenever we are talking about dual effect, the dilemma is to find a balance between control and communication. This controller has two jobs to do. It has to pass on some information about x0 to the policy such that y2 can make a good policy choice and hence try and go for an minimize the cost to the best of its abilities, and at the same time the policy gamma 1 should not be too much that the direct cost gets affected. So this policy has two things it has to balance between. One of them is control and the other is communication. Now so far in this course we have talked about two kinds of problems. Sorry, actually we have not talked about kinds of problems. We have generally talked about one particular version of it where the focus was control. For example, we talked about MDPs or we talked about POMDPs. We talked about various examples of all of that. And in all of that, it was that the information structure was classical. In problems where the information structure is classical, the main focus is control. All that matters in these problems is control. There's no need for a communication as such. Because in classical information structure problem, for example, gamma 2 would have x0 as information available to it. If it is available to gamma 1, it will also be available to gamma 2. That's what it means for it to be classical information structure. And since it is already available, there's no need to communicate it in smart ways like Witsenhausen's counterexample does. So there is no need for a communication because the needed information, whatever that is available to the sequential controllers. That's one kind of extreme of Witsenhausen's example. Now the other extreme is if we have a situation where this doesn't matter, that the cost does not have a direct dependence on u1. The cost only cares about x0 and whatever is here. Or the other class of problems which are called communication problems. In problems with communication, it's control that's not going to matter. All that will matter is just communication. It will be pure communication. So here, control doesn't matter. And the main thing to note is the reason why Witsenhausen's counterexample and similar variations of it are difficult is because it lies in between these two extremes. Because it lies in between, it needs to find a balance of control and communication. if it relies on one side more, the other side will affect the cost, and hence it will not be optimal. Because of this duality of the problem, it's harder than either of the extreme cases. So in this week, the focus will mostly be understanding a small class of problems from communication, which can be framed similar to decision making, and where we can see what information structure even means. So this is looking at problems from communication, but with a different viewpoint. So this week will not go into details of many different communication problems and their solutions, but just the core ideas for one class of problems. Okay. Any doubts so far?
No.
Okay, perfect. So this is one kind of communication problem. So here what we have is there is a source which wants to communicate some information to the receiver or the destination, but to do that it has a medium available, and the medium has some restrictions, meaning maybe the medium is via email, and hence it needs to make sure that whatever is the source comes to it in a format that the channel can take as an input, and further on whatever output it gives can be decoded to the same form as the form of the source. So in typical communication problems, the objective is to make sure that these two are as similar to each other as possible. So there is a distortion function D, which takes S and S hat as the inputs and gives us a real number, a positive real number. For example, it could be mean square error type of distance, L2 norm, or it could be an indicator, just maybe sort of like keeping a count of how many times S and S dash or S and S hat are not matching, something of that sort. And the objective is to minimize this distortion, the expected distortion. With respect to FNG, so the things that we have in control, the things that are for optimization are the encoder and the decoder, the functions, the encoder function and the decoder function. So if we were to draw a parallel between this communication problem with the kind of sequential decision problems that we have seen so far, we would say that okay. So we would say that since the optimization is with respect to FNG, these are behaving very similar to policies. This is what there is any control over. This is what the optimization is done over. So FNG are the policies in this problem. If these are the policies, that means finding the optimal encoder decoder such that this quantity is minimized is the same as finding the optimal policy of the problem. Remember, policy was a function for us even in control, so it's a complete parallel so far. There's nothing wrong here. So optimal encoder decoder would be giving us the optimal policy. Now, if this is the kind of things that we're talking about, the next obvious question would be, uh, can we say something about the information structure here? Is there an information structure in this problem? So, since the job here is to pass on S to the destination and have S hat match S, meaning at the destination S is not known. Or rather, one step back, the decoder also doesn't know S. Because if it knew S, there's not a real problem. It knows S and it can just use that to find S hat by default. That's not much to do. Meaning, G would not know and this is how typical control communication problems are. The decoder doesn't know the source, otherwise there was no need of an encoder or a medium. There wouldn't be any such things. On the other hand, the information of G is Y, right? So what G knows is G knows Y, and F knows S. And see, Y is something that depends on X, and X is something which is F of S. So indirectly, Y G has dependence on S, but it doesn't know S. So we can say this is not known. There's no such information available. So with this kind of a reason that G needs to figure out S, but it doesn't know it. It depends on S, but it doesn't really know it. And hence, this is actually the same as a dual information structure. A non-classical information structure. But remember, our goal in a problem like this was to minimize this distortion function uh, by minimizing over f and g. So it doesn't depend on x or f. The goal itself doesn't depend on it. Meaning, if we compare it back to Witsenhausen, it doesn't have this component at all. This component exists, but there's no component of this kind. So all it is doing is focusing on communication, and it's not bothering with control whatsoever. It doesn't need to. And what that does is there's no dilemma in communication problems of the kind of Witsenhausen's dilemma, because it doesn't need to try and restrict what kind of U can be used or what kind of a policy can be used by controller 1, such that the cost doesn't get affected by it. Because here in this problem, the cost does not have dependence on the policies or the FNGs. To be more specific, it doesn't have dependence on F. That's the main part. And hence, it doesn't have the problems similar to Witsenhausen. meaning there's no dual effect. Okay, so this was to point out the similarity of Witsenhausen's problem with a class of communication problems, and at the same time point out why communication problems are an extreme of Witsenhausen's problem. It doesn't have, even though it has non-classical information structure, because it doesn't have dual effect, meaning it doesn't have the dependence. It the policy does not affect the cost. The dual effect isn't present, and it's an easier problem as compared to Witsenhausen's problem.
I have one question.
Mm-hmm.
Just
Yeah, yeah. Tell me.
this. Wait, I'm getting echo.
Yeah.
In the communication problem, in 5G case, we have this X bounding, like channel capacity.
Mm-hmm.
So in that case, let's suppose I'm putting minimum of expectation DFS comma S cap such that X is less than some X naught. Capital X is less than X naught. Okay, now when you put the Lagrangian equation to minimize that, it becomes lambda times of x minus x naught.
Yes.
Now in that case, it is actually because in real world when we design a system, we cares the capacity of the channel as well as the encoder decoder.
Yeah. So in those types of problems, see, you're changing the goal. Then the difficulty increases. The
Mm-hmm.
dual effect shows up. It's not the same kind of dual effect as you see in Witsenhausen's, but a version of dual effect shows up, and hence the difficulty of the problem increases. See, by saying that this is easier, I am not saying all communication problems are easier. This is just one version of it.
Mm-hmm.
The goal that is chosen here is simpler than, this is more like a toy goal. This is not always the only goal. There are restrictions, like you're saying. There can be restrictions on X. There can be restrictions on the number of input slots that are allowed, and so on. All of that is there.
Okay.
Okay. So now let's go through how people in communication theory deal with these types of communication problems. So we're going to this is going to be very surface level, very just touching upon some of the core ideas from there to just compare and contrast. You'll not, this is not a course on communication theory, so the focus is not on these things. The idea is to be able to come back and compare it to Witsenhausen's or with other standard problems in control. So with that in mind, make sure you understand that this will not be a complete description of things from information theory or communication problems. So now let's look at how these types of problems, problems of communication, are dealt with in standard theory. So one of the ways of doing it is by sending the same source signal again and again through the channel and letting the decoder figure it out and the receiver get the correct information. That one is called repetition. That's the easiest way of making sure that your error is reduced, your distortion is reduced as much as it can be. But Shannon was one of the people who said if we are allowing the use of channel over an extra number of times, not just one but a sequential number of times, then what can be done is something even smarter, which comes under block coding. So the idea of block coding is, instead of sending one message, encoding and decoding it, and then uh, comparing the obtained S hat with the original S, what is done here is a block of messages are sent, or a block of symbols are sent, and let's say the length of that block is n, so there are n of those. Our encoder function, the f, now let's say it has dependence on n as well, as in what is the number of messages that are being encoded. So let's say it converts these SN messages to some XK messages. So it starts from X1 to some XK. Okay. Then let's say that the communication channel keeps the length same. So if it got X1 to XK, it's going to keep the length same and convert it into some Y1 to YK. And finally, the decoder is going to get these y1 to yk and convert them back into messages of length n, as they were in the beginning, and obtain some s hat to sn hat. And the idea in block coding is to try and minimize this quantity. This quantity is the probability that s1 to sn is not the same as the hats, or what is sent by the source is not the same as what is received by the destination. Notice here, I'm not saying one of them doesn't match. I'm saying if the whole thing doesn't match, then that's the probability we're looking for, and that's the probability that is to be minimized with respect to some f and gn, or we're supposed to find out some f and gn such that it can it be minimized. That's the kind of questions people in information theory generally ask. And notice, we can write the hat s1 hat to sn hat in terms of the function gn. Now, just just to show that this problem also has its own challenges, that this is actually not a very simple problem. Consider the channel. This is the channel. So here, this particular quantity is saying what is the probability of seeing a realization of y1 till yk given x1 till xk was inputted in the channel. Okay, so this quantity is going to, it is going to seem to come handy if we are trying to understand these things.
Actually, this is the most beautiful way to represent channel, in my opinion, because
Okay.
based on experience.
Okay, why is that?
Because it simplifies a lot a system. Because now all the systems, if you don't consider, there are so many complicated design there. Everything boils down to simplest form like this. This is the most beautiful form to represent a channel.
Okay. I mean, it is fair. So, uh, one simple example of a channel could be the following. Let me draw it here.
Because by nature it is having distortion in it. It's capturing all possible distortion in that.
So, okay, let's take one example of a channel. So, this is more like a toy example, nothing more than that. Suppose x is 0, 1 and y is also 0, 1. So, a channel could be something that, say, sees 0 and with probability p lets it be the same for y, and with the remaining probability it actually flips it. Okay, so that's 1 minus p. And the same thing could happen to 1 also. Let's say we're keeping the probabilities same. So 1 stays 1 with probability p, and it flips with probability 1 minus p. So in that sense, either the channel can be represented, in the form of a diagram like this, or what I have managed to say in all of this diagram is the same as the equation above. And right now, when I'm saying it, I am only using x and y. I'm not talking about x1 and y1. So what I have represented here is the information. Yeah. For any particular realization. Or all of that information is captured here. We can go from one to another quite easily. Like we can create such a diagram if we had this distribution, or the other way around. Is this what you were trying to say?
Yes, exactly. It will become a matrix, and that
Yes,
matrix captured everything.
exactly. And, and since it's boiled down to a matrix, it's much easier to handle.
Exactly.
Yeah, okay, good point. Alright, so now let's continue. By the way, this is just one example. There are many different examples of communication channels. If you're interested, you can look into which reference? Elements of information theory?
Thomas and Cover elements of information theory.
Yeah, information theory. Okay, anyways, now let's continue. So, what we had earlier was this. Our ultimate aim is to find out what is the probability of error, and we want this type of an error. Which is actually the same as looking at the probability of error and putting weights of getting a particular message. So right now the whole thing S1 to Sn is denoted by some symbol M. It just means that this is called as one message. So if what is received is not the same as M, then what is the probability of that? And we're taking the weights with respect to S1 to Sn being equal to M. So this is the same as the situation of 1 minus these two being equal, right? And for this quantity to be equal to M means the inverse mapping of Gn would be for this particular M, and at the same time Fn of M would have produced some X for us here. So ultimately, to minimize this quantity, we can only focus on this also. To minimize this quantity, one needs to focus on getting the correct G and F. So a problem of this kind is actually not that easy to handle, not in a straightforward manner. The way this is handled, at least in a subclass, specifically, for example, if we're talking about data compression, which means we are now focusing on a situation where our medium has certain properties, meaning one, it is noiseless, and two, the number of input it allows is now restricted. For example, the source is a binary n input object, so this could be 2 to the power n different values. This could end up having 2 to the power n different values. Alright. but our medium will only allow 2 to the power k inputs, assuming k is less than n. If k is greater than or equal to n, then that's not an issue. But if it is less, then the medium can only focus on a much smaller number than what the source wants to pass on. In such a problem, can we talk about the probability of error? So, to talk about the probability of error, specifically in the scenario where k is less than n, what needs to happen is um f needs to be a one to many mapping, meaning from x, sorry, no, from the source, many of them would get mapped to the same x value. So maybe x1, x2, and so on. But the decoder g function, which would have received the y's, will only be able to decode one of them, not all of them. If that can be done in a meaningful way, then we can talk about compression, and then we can talk about, finding the right um, encoder and decoder for the problem. And recall, right now we're focusing on the situation where the cost or the goal of the problem is to minimize the error, the probability of error, and the minimization is done over the encoders and decoders. So in this scenario,
There is a representation recently I read. It's like in compression, data is lost, but the information is shared. So maybe we want to compress the data dimensionality so that at least information is shared. Something like that.
yeah, so if we were to, so whatever I'm going to talk about further on, if I was to say it in just a sentence, what is happening is data compression basically focuses on information that is of high priority. Now, what high priority means will become clear eventually. Only that part gets encoded and ultimately decoded, because that's of higher priority, and that is used to recreate the same thing. Not the same thing, maybe, but that's used to talk about this being the minimum. It eventually comes from entropy and AEP and so on, but yeah, we'll get to that. The idea is not all of the information in the messages has same priority. Some of it may be of more priority, and those are the ones that should be encoded in a careful manner. So for those, it needs to be a one-on-one mapping, and that particular mapping G should be able to decode. If that happens, the error can be minimized. And for the ones which are not even mapped, there can just be a simple declaration that okay, these were not even mapped, these were left out completely. And that's the idea that actually comes out of this whole thing also. Yeah, I thought you had a question.
No, no, no. Yeah.
Okay. All right. So, in this scenario, the question that Shannon had asked was, so is it possible to construct fn and gn for every value of n such that in the limit n tends to 0, this probability of error becomes 0 itself? So the question it's asking is, for every n, assume that we are going to the asymptotic limit, that we are looking at very large n, meaning the block that was sent was very large, then can the the what is the part that is sent and the part that is received, the probability of that happening, it matching, should almost tend to 1, or rather it, the error should tend to 0. Or in other words, the same question can be asked in a slightly more relaxed manner by saying, okay, let's say there is some epsilon which is greater than 0. Does there exist some encoder decoder fngn, and n is large enough in that situation such that the probability is bounded by this epsilon? Okay, so these are the kind of questions that were asked in this line of work. So now notice, if we are talking about taking n to infinity, or talking about asymptotics or large enough n's, and we keep the k fixed to say, let's say 10 for example, then if you keep increasing n but you're not changing the amount of input that can go through your channel, this probability can never be 0, even if you increase n to whatever number you want, to whatever asymptotics you want to take it. This can't be 0 because you have a very fixed cap. On the other hand, if you allow k to also grow in some correspondence with n, still k can still be less than n, but if you just allow it to grow, then what happens? That's the real question that's being asked. They're not taking the scenario where k is fixed. So let's consider this particular scenario. So let's say k is some theta n, and theta is less than 1. So k is definitely less than n. So we're in a fine range. So now consider this, 2 to the power k divided by 2 to the power n. This is number of encoding inputs allowed compared with the number of messages that are possible, n string messages that are possible from the source. Since theta is less than 1, this is a negative quantity. 2 to the this is a negative quantity. So this is going to tend to 0 as n tends to infinity. So what is being said here is, the size of such the size of what is allowed is still small as compared to the bigger thing, but the probability that there is an error is bounded by some by some epsilon, or if you take n to infinity, the probability of error goes to 0. So now it's if it was to be written more carefully, it's basically saying, consider some epsilon, and now it's asking, does there exist a set, let's call it an of epsilon, which is a subset of this. So this is a subset of the source, which will occur with probability greater than 1 minus epsilon, but its size, the cardinality of that set as compared to the full set, would be very small. So pictorially, this just means we are asking, if I were to represent this on a number line. Let's say the whole set, this whole set, okay, so instead of this whole set I'm taking some interval, this much, let's say for example. Then is there a section which as compared to the whole thing is very small but has a very high probability? So the probability here might be something very large. Something like this. This is the probability. Does there exist such a set is what is being asked. So even though in first glance these two seem contradictory, they're asking if we can find such a set which satisfies both of these properties. So there's one setting in which it is possible, and that's the setting of a typical set, and that's the description now. By the way, any questions so far? Is the contradiction clear?
And you know, this contradiction is highly dependent on the source. It clearly says that source is correlated because that set is highly probable. After that, it's not. Some kind of correlation exists. Complete independent source is very horrible to deal. Like all even uniform probability distribution, it is then compression will fail.
Because then everything is equally important, right? Here we're
Yeah.
pretty much saying, is there some part which is more important than everything else?
More important. Yes.
That's what it means to look at the distribution of a part.
I have a contradictory view that I'll share in the last of this our tutorial.
Okay.
It's from Stephen K. and this Kaushalya Adhikari, two different people who has proposed a different view of this. But in the last, I'll share.
Okay. Okay, we can talk about that at the end, like you're saying. Okay, so let's continue. So now we are asking, can there be a set which is much smaller as compared to the set of things available from the source, but the probability of seeing something from that set is very high, or yeah, it's quite high. So to answer this question, let's consider the scenario where we're taking these x1 to xn from binary, and each of these xi's are IID generated, meaning they are independent of each other and coming from the same distribution. Then the probability of this whole thing is the product of probability of each of them, and since they're coming from the same distribution, we could write it using the same p. So one example of this could be if suppose you're saying that the probability that x1 is 1 is denoted by some p, then what is the probability of getting a string like this? So that would be, there are 3 ones, meaning it's a p to the power 3 thing, and then there are the remaining are zeros, so that is 1 minus p to the power 2. That's the probability of getting this string. Here each of them can be 0 or 1, and it's 0 with probability 1 minus p and 1 with probability p. Now if p is equal to half, then any string you look at will have the same probability. Let's say we're looking at strings of length n, so all those strings of length n will have the same probability. On the other hand, if this was not half, then each of them will have some different probabilities. Some of them will have same probability, but there is some variation in probabilities, and it's this thing that is of use to us, that p is not equal to half, that we are allowing there to be some non-uniformity. Only then we can find such a set. In a general case, there might be other scenarios. So, the asymptotic equipartition property says that a typical set is defined as follows. A typical set is an of some epsilon, which is a subset of the binary 0 1 n times. So it's a n bit set, subset of that. And it's called a typical set if for all of these x1 to xn, which are from this set, the probability of getting this thing, getting the exact one string, exact message, let's call it message at this point, yeah, getting this exact message is bounded by these quantities, where hp refers to entropy of p, which is, since it's a binary situation, the entropy has the following form. Remember, we have taken the situation where each of these comes from a Bernoulli distribution, right? Bernoulli P distribution, to be more specific. And it's 1 with probability P and 0 with probability 1 minus P. So now we can focus on this component again. And we can take a log on both the sides. Log base 2. Recall, these xi's are all IIDs, meaning it's the product that matters, and hence we can write it as a summation because we've taken a log of that. And we can remove the n's from both sides. So now this quantity is bounded by entropy and some epsilon. Both upper and lower bounds are there. And notice what is HP. HP is this quantity. We can always rewrite it as follows. Okay, now I'm giving an example of a typical set in the current scenario. So, say you have a situation where there are NP number of ones. That's the average number of ones you'd get. And if that is the exact number of ones you have in your string, and the remaining are zeros, then the probability of getting such a typical string would be p to the power np and 1 minus p to the power n times 1 minus p. And if you take the log of this, you get minus n of hp. So a typical set is exactly this. Well, one example of typical set in the current settings that I'm talking about is this situation where the strings are such that number of ones are equal to the exact value of the average number of ones, and similarly number of zeros. And such a typical set has a few properties. When n is large, the probability of getting something from the typical set is quite high. So the probability of not getting something from this set would be quite small. And the size of this set as compared to 2 to the power n, we can find out what that is. And it's bounded, it's upper and lower bounded both. So far, what I've done is I've talked about. Okay, let's take a quick recap of what we've done so far. So, we started talking about communication problem. In communication problem, we are talking about how they typically solve it. What is the standard way of looking at a communication problem? So, we are looking at block coding, meaning a block of information is sent from the source, and that is to be decoded by the decoder, and uh, the receiver gets it, and then they compare if they got the right thing or not. So, one of the sub problems where this problem can where you can find the optimal encoder and decoder can be solved is the scenario of data compression. So in data compression, you're basically saying the medium has limited number of input slots and hence same number of output slots also. So only a part of the data can be encoded. The remaining needs to either be a many to one encoding or it can't be encoded. So in that scenario, what we are focusing on is is the following question. And the question is it possible to construct encoder decoder for each n such that we can asymptotically we can make the error go to 0? And see, this question converts to finding a subset of the source which has a very high probability, but its size as compared to the whole thing is very small. Or rather, when n goes to 0, the size tends to 0. Sorry, as n goes to infinity, size tends to 0. So there is one way of finding such a set, and that is called the typical set. And it's in the scenario where these x's are actually IIDs, so they're coming from the same distribution, and x1 and x2 or xi and xj are independent of each other, and the distribution that they're coming from is for now assumed to be Bernoulli. Then they have a property that the probability of getting a string of length n from this typical set is bounded by the entropy, is related to the entropy of P. And we saw how that actually happens. And these are finally some properties of a typical set. So now the next thing here is data compression even possible? What we are starting out with is we are starting out with some binary zeros and ones, n of them. So it's an n string block length, n string block, which is being encoded into something with k strings. So this must be that k. And on top of that, we are augmenting one bit information along with it. So f has the following form here. If the string that is obtained is a part of the typical set, then make this added bit 1, and that label is useful, that is attached. Otherwise, if x is not from that typical set, then make this extra string 0 and then nothing else is attached, meaning it's telling the decoder whether it can decode it or not, whether it's been encoded properly or not at all. So what G would do is, if it sees that this bit is 0, then it will not have an answer, it will not be able to decode. So sorted there. But if it sees a 1, then it's going to decode. And it's going to deconstruct and find out what is the string x1 to xn. Meaning, in this scenario, with this type of a setup, the probability of error is basically the probability that x1 to xn is not the same as what was seen. This would only happen if x1 to xn is not lying in the typical string, because if it was lying, then reconstruction was possible. That's how it's been designed. And this happens with the probability of epsilon. Remember, the opposite of this happens with the probability greater than or equal to 1 minus epsilon. So this will happen with the probability of epsilon. Which means if our k is greater than or equal to n times hp, then the receiver can get the source's information with no error. If that's not the case, then there is a problem. So what this means is, if you have a binary string of length n, or you have n bits available to you which are generated from some IID distribution, from a Bernoulli IID distribution, then it can be compressed to a length n times hp, whatever that p value is. Such that the probability of error will tend to 0.
Just an extreme case, can you put HP is equal to 1?
Yeah, hp equal to 1 is this, no?
Then K is greater than N. K will be greater than small n. Means no compression.
Yeah, that's not compression.
Okay, my bad.
Yeah, that's not compression, right? If you're already putting p equal to 1, means you're specifically saying everything that's coming out is 1. You know exactly the string that's being sent. There's nothing there. It's a deterministic
No.
thing.
Actually, I got this wrong because when P is 1, then HP will be 0. So it's my mistake.
Okay. Alright. Now, what if it was the opposite? If k is less than this, then the probability of error jumps to 1 directly. So there's no slow movement. It's a phase transition type of a situation happening here. Meaning, if the limit of your channel is smaller than the p you're using in your Bernoulli distribution, then there's a problem. So you'll have to tune the p properly so that it doesn't happen. This is the converse theorem, which says if your theta is less than hp, then the probability of error will directly become 1. Okay, so what we have done so far is, where were we? So we converted our question to the existence of a set which has the following properties. And then we said there is something called a typical set which has both of these properties, and we were talking about a specific setting which is where all of these quantities are zeros and ones, binary bits. And we were talking about IID, that they're sampled from an IID distribution, an IID Bernoulli distribution with probability of any of these being 1 is equal to P. So in that scenario, we saw that if these types of bounds are possible, then you can find a typical set. And this typical set would be such that for large n's, obviously, the probability of getting such a typical set would be greater than some 1 minus epsilon. The size of the set itself will be bounded. And if we take n to 0 in this situation, it would tend to 0. This is the asymptotic equipartition property. So then the next question that we are asking is compression even possible? And for that, we're showing like a toy way of saying that yes, it is. Here, to make sure that the error is 0, we're augmenting one extra bit. That one extra bit has the information whether the string that has been observed is from typical or atypical set. If it is typical, then that gets encoded properly to something and can be decoded, and we can get a reconstruction for the original x1 to xn. On the other hand, if it is not from the typical set, then the extra bit would be 0 and that can't be deconstructed, and that's where there'll be an error. An error is declared, nothing is decoded by G. And if that happens, there's no hats, so that part of the error will not show up. The only error that will show up will be the error in deconstruction, and this will only happen for the case when what string we observe is actually from the atypical set, and the probability of getting something from the atypical set is actually very small. Okay, so what this means is, as long as our k is greater than n times hp, the source can be recovered, and meaning the data can be compressed. Okay, now right, with this I think we're almost done. So now this is more like a quick comparison between the communication problem that we saw. We just saw one subclass, one specific problem, not everything that's there in communication theory. And we saw the similarities of that with Witsenhausen, in the sense that communication problems are also the ones with non-classical information structures, but there are differences between the two problems. In Witsenhausen's problem, the objective included a term that was affected by the controller directly, also by the policy directly, but in the communication problem there's typically no such term available. Apart from that, in Witsenhausen, the source is a scalar quantity. We have x, 0 and so on. Those tend to be some scalar quantities. But here, the source is actually a block. And we are interested in asymptotic properties. We are not talking about what happens for a given value of n. If we were to focus on one given value of n, then that would actually be a combinatorial problem. So this is one difference. Here we're talking about a scalar quantity. We could have the source coming from some vector also, that is fine. But we'll not let that vector be of infinite dimension. That much will definitely be the case. But here in communication, what is typically happening is some n amount of information is being sent by the source. It is being encoded. The channel sees it, then gives some output, and then it's decoded. So, in all of the middle process, what is happening is it's similar to accumulating all that information together, seeing a pattern, and then using that pattern to decode it. On the other hand, in control, there is no such uh, thing that happens. And the reason is, if we were to wait for a large n, then the distribution itself will change. So the problem would take a very different form. So even though we're saying that communication problem is an extreme case of Witsenhausen problem, they are structurally quite different. Nevertheless, it seems that there is connection between these two problems since they have similar information structure. So information does play a role in control, and that was the idea that was shown throughout the course. So with this, I have covered the things from this week's lectures. If you have any doubts, we can talk about that.
This thing, right? The professor was telling, uh, like communication setup is very important for a control system because of information sharing. That that statement, and to understand the information, this information theory may not help because this is for a different purpose at all. Don't know, but it's a very good view. I enjoyed this view actually.
No. So it's true. What is being done in information theory may not be of direct help for control problems where information structure matters. The point is, these two have been studied separately as separate streams. The middle area, the merging of these two, is actually a very difficult problem class, for example, Witzenhausen itself. And that is like an open research area. There's a lot of problems there. That was the core
Recently,
point he was trying to make.
recent, yeah, recently I saw people are trying to use because the intersection of these two are like fake information. Like, how do you control the fake information, or like societies and some kind of fake information actually spread a lot. How do you control there? The control different controllers are sharing different information. Some informations are fake or modified. I saw this research is very, literally, it's very hard to tackle. And I wanted to share this second view. What is happening is in communication domain, there are two school of thoughts.
Okay.
One school of thought we presented in this course, which is about how do we compress in that compression area high probability data or high probability source generator, which has more, like we know that if something is rare event, we don't transmit, it doesn't matter. It was a very low thing, common sense. But there is another school of thought which talk about redundancy addition. They'll add redundancy.
Okay.
We call as source coding and channel coding. So
Okay.
whatever this is we discuss, it's a source coding part. There is another domain in same communication. It's a channel coding where we add the redundancy and increase the number of bits for transmission purpose. So I'll share my screen for a second thought.
Okay.
It's a very different school of thought itself, which treat an information in a different way. So this the authors are very renowned authors. Stephen K. and Kaushalya Adhikari, very big people in signal processing communication. For their point of view, the second school of thought, the information is something which is low probable event. So, for example, Jupiter should rise in the morning instead. So that then that occurrence being of non-zero probability. So should provide much information. Thus, the amount of surprise, like the amount of surprise, the low information or low probability event has more information. This is a core thought process behind that.
Mm. Right.
So this is second school of thought which consider like low probable event has more information packed in it because it's a rare event.
It has uh, more of a surprise element, so entropy will be
Surprise.
affected by it. Yeah.
Exactly. And surprisingly, entropy fits for both school of thought. I don't know why I'm very excited, but this I don't know. Shannon was the intersection of both or what, but he somehow cracked this element who's an intersection of both school of thoughts. I think that's why he's a father of communication, modern communication.
Mm.
So that's what I was telling. There is a second school of thought which is considering like less probable event or less probable states has actually a very good information hidden. Another school of thought consider who wants to compress the information. They consider as a high probability event you consider as an actual typical set or data to transmit. Rest you ignore.
Hmm. Yeah, the purpose may be not data compression. The purpose might be something different in those settings. That's when the rare ones matter. The atypical set would matter in those situations. Maybe that's the idea they're going with.
Kind of. But
Hmm.
in current 5G, what we are doing, we are using both. First, we take the data, we compress first, then we add redundancy before transmission.
Okay.
So, so we do both actually. The same encoder has a both job, compression as well as adding redundancy. So it is more complex now.
Right. Okay. Do you have any other doubts?
No, it is very good course actually.
E-
Thank you so
okay.
much.
Yeah. All right. Thank you. So I'll end here. Um, this is the last tutorial also. So if you can think of any doubts and you want to discuss something, we can. Else, I'll end the session.
Yeah.
Okay. Perfect then. Thank you so much. Bye bye.
Thank you. And for this no robot, this fear thing, I still am reading phase.
Uh huh.
Maybe
Okay.
I'll my findings I'll share you email through
Yeah.
email. I didn't complete properly. I did not get time proper. So
Not an issue. Not an issue.
um,
Once you've gone through it, do share.
perfect. Thank you.
Yeah. Okay. Bye bye. All the best. Bye bye.
Yeah. Thank you.